All right, this is number 5 from the Thermo review. Well, they tell us that for this reaction up here, the reaction is thermodynamically favored. So that's pretty useful information right there. That tells us that delta G is negative. And they tell us that the delta H is negative as well. So it's an exothermic reaction. Then they say predict the sign of the entropy change delta S. Now normally, I like to use the Gibbs-Helmholtz equation to kind of think this thing through. If we know the sign of delta G and we know the sign of delta H, maybe we can predict this. But in this case, I don't think that's going to work. And one of the reasons is because when we're talking about the entropy term going up or down with temperature and changing a reaction to become spontaneous, we're assuming that the reaction will become spontaneous or will become non-spontaneous. But here, we don't have any hint. It could be spontaneous all the time. They're just telling us that it's thermodynamically favored at 298. So I don't think that this approach is going to work. So we're going to go back and just look at the reaction here and say, well, there's 2 moles of stuff over here becoming 1 mole. That's one thing. And also a gas is becoming a solid. I think definitely there's an increase in order here, so the sign of delta S will be negative. So here's what I've come up with. Delta S is negative. Get to the answer right away. And then the rationale, because 2 moles of reactants becomes 1 mole of product. So given my evidence from up there, showing an increase in order. Love this word, use it all the time. More order, less order, that kind of thing is really helpful. This is really short, but I think it's enough. We've provided specific evidence. You notice I didn't talk at all about the gas becoming a solid. If you wanted to be really thorough, you certainly could do that as well. And you might wonder, if you just talked about states, would you get the point? You might, you just need some evidence. It's always best to be more thorough, but I think this should cover it. B says, what is the sign of delta G at 298? Explain. Well, I think I'm simply going to say the reaction, since it was at 298, was thermodynamically favored. I think this is enough evidence for us to say that delta G is negative. Delta G is negative because the reaction is spontaneous at 298. Something feels wrong about such a short answer, but I'm absolutely sure that that's the evidence that they want us to use, so we'll call it good, be done, move on to the next. Part C is probably the question we were predicting from this line of questioning. They want to know what change will occur, if any, to the value of delta G as the temperature is increased from 298. So this is where we want to think through the Gibbs-Helmholtz equation. We already know the sign of delta G. We know that it's negative. We also know the sign of delta H, it's negative. And we know that the sign of delta S was negative as well. This was an unfavorable entropy term. This was a favorable delta H term. So I think temperature is going to have an impact here because we're having a battle between favorable and unfavorable terms. So we're going to want to decrease the magnitude of the entropy term. So that means lowering the temperature will decrease its influence and allow this favorable enthalpy term to give us a negative delta G. Okay, so here's my written explanation. As the temperature is increased, the delta G value will become less negative. Remember, it's becoming less spontaneous. So if it was negative 100, it might go to negative 50. It's becoming less spontaneous, so therefore less negative. And I tried to go back and make sure that I was reading their prompt and answering it in the way they wanted it to be answered. So that they were talking about as the temperature increased. So that's what I started with in my STEM. So give the conclusion first, then the rationale. Increasing the temperature increases the magnitude of the unfavorable entropy term. So if T goes up, delta S, the entropy term becomes more unfavorable, causing the reaction to be less spontaneous. Boom, and you're done. Now, of course, the other way to tackle this is to go and talk about the math with the signs, right? If this is negative, a negative times a negative is a positive, and if this is a really large term, it'll end up with a positive delta G, and that's a perfectly acceptable way to do it as well. In part D, they want to know, as the reaction takes place in a closed container, so obviously no gases can escape, what changes will occur to the concentration of CO2 and the temperature. Now, I really love the part of the question where it says what happens to the concentration of CO2, or you could ask pressure. The temperature one is not so great of a question. They should have been a little bit more specific. Remember, this is not an AP test. It's just a practice one. And so let's start with the CO2 since that's the one that works out better. Well, you notice that CO2 is a reactant, so as the reaction goes on, we'd expect the concentration of this to decrease. So that's pretty straightforward. So here's what I wrote. The concentration of CO2 would decrease because it is a reactant and it will be consumed. I think that that's enough. They just want you to notice that from the reaction. The temperature, on the other hand, is a little bit more tricky because I have a sneaking suspicion they're just trying to get us to notice that, you know what, the delta H is negative. It's an exothermic reaction. And I think they're wanting to say the temperature would go up. And of course, you would be talking about the surroundings in that case. So that's what I don't like about this, is whether you're talking about the system or the surroundings. And I've looked up on the key here, and the authors of this problem did intend that. They said the temperature will increase as heat is given off by the exothermic reaction. So that was the piece of evidence there. And I'm not going to write that, but because it's a simple explanation based on that piece of evidence.